So our last talk of the day is from Erica Molnar Bufanda. I think, hopefully I've pronounced that approximately right. You're a first-year postdoc at the University of Edinburgh, but you've got your PhD at the University of Hawaii, so that's quite a changing climate.
All right, thanks everyone for sticking around for the last talk of the day. My name is Erica. I'm now a second-year postdoc at the Institute for Astronomy at the University of Edinburgh. I have to think about that for a moment because I used to be a graduate student at the University of Hawaii, but they were also called the Institute for Astronomy. And they also abbreviated the IFA there, and they're also located on a hill away from the university. So it's almost like going to a different dimension here, but very similar circumstances. I also want to say that it's been a real delight hearing so much enthusiasm for comets, being surrounded by so many comet nerds. It's just been really great, and all the images have just been very inspiring, and I thought I would contribute my own astronomical image that I took. So. Believe it or not, this was actually taken from Blackford Hill here in Edinburgh, close to where I work at the Royal Observatory Institute for Astronomy. This is an iPhone image of 10-second exposure. So I was a bit shaky because, as you may or may not have noticed, my accent is a wee bit different from mostly everyone's here. So I am actually coming from Hawaii. So about almost exactly a year ago, I made a very extreme island hop from Hawaii to the UK to start my postdoc here after I got my PhD. And my hands were a little bit shaky because I was not used to the cold temperatures. Very spoiled in Hawaii, where it's about an average of 27 Celsius year-round. So that was a real fun time. But as you can see, even here in Edinburgh, we can get some really nice cometary images if we're really lucky and the sky cooperates with us. And here's another one too. This actually, I didn't say what the comet was. It's C2023 Tsuchinshan Atlas, I think. Yes, C2023A3, taken almost exactly a year ago, I think in late October 2024. It's a really nice way to start my postdoc, going up to Blackford Hill and seeing a naked eye comet in Scotland, so I was very lucky. Going off to, I kind of skipped through my intro slide, but essentially what I'll be talking to you guys today about is cometary modeling. So using a suite of observations from both professional telescopes, amateur telescopes, all-sky surveys, to construct a comprehensive light curve or a comet's brightness evolution over time, and then using that in conjunction with an outgassing model to retrieve comet properties for a population of targets. And the idea is to do this systematically because of the fact that we're discovering 40 to 50 active bodies per year, and that's just going to increase with the development of LSST, as you've just heard from Jamie. So, starting off with a very brief review, I know everybody here is mostly an expert in this, but comets themselves, we know them as those tiny little conglomerates of ice, gas, and dust. You know, you have the porous medium of the nucleus that has grain families, different sizes, making up the interior, different layers of both grain sizes and ices or volatiles of different types. The most prominent ones are water, CO, and CO2. And what is happening in a cometary orbit is you have this icy, dirty little nucleus that is about approximately 1 kilometer on average in diameter. It's most likely irregular. So for example, the image shown here is 67P, which was imaged in situ in the Rosetta spacecraft mission. And you have a small icy body like this, and what happens is if it's far out in its orbit, a lot of these active bodies, as you already know, have eccentric, stretched out elliptical orbits in comparison to the planetary counterparts in the solar system. And so when it's entering the solar system from aphelion or furthest approach, it starts getting hotter, the temperature increases, and what's causing these dust tails to form in all of these spectacular images that we've seen all day is the process of sublimation, or the ice to gas transition on the surface and also subsurface of the comet. So what's happening is the temperature increases, that's causing that ice to gas transition. It's lifting off dust grains in the process, and that's what's causing the dust tail. And that effect becomes more prominent as the gets closer and closer to the sun and reaches its perihelion or closest approach. And so shown here, I think, is Comet Hale-Bopp. And I'll be mostly focusing on cometary activity in the context of the dust tail, not the ion tail, just because I'm not an expert in that. That has to do with the magnetic field, and I don't know too much about that. So primarily be focusing on the dust properties of the comet in the context of activity. So I primarily study comets that are from the Oort cloud. So Jamie gave a really nice review of the different types of solar system formation theories. If you come away from this mini conference with any knowledge about solar system formation, the one thing to remember is that it was very chaotic. It was a mosh pit of sorts, right? You have like the protoplanetary disk, a mixture of that primordial material of gas and dust, and some of it coalesced to form the first planets. Some of it was flung outward to the outskirts of our solar system, where it gravitationally settled and was kept in cold preservation in the Oort cloud for billions of years. The Oort cloud itself, and so this is an artist's rendition of kind of that process, or that kind of icy debris field that exists on the outskirts of our solar system. It's kind of that relic of that tumultuous time, which was our solar system's birth. And what happens is all of the years up until the present, the effects of the galactic tides of our galaxy, as well as passing stars, both of those processes have the ability to gravitationally disturb or perturb some of that icy material in the Oort cloud, send it flying back inward into the inner solar system, where we observe it for the first time as a comet. And that's why a lot of these comets have these really eccentric orbits. And specifically, when a comet enters the Oort cloud for the first time, it's often called a dynamically new long-period comet. And the very loose dynamical theory, and I say this loosely because there's a full entire field dedicated to this research, but loosely speaking, what the theory is that you have a dynamically new comet coming in, and when it comes into the inner solar system, it encounters kind of a gas giant or one of the terrestrial planets. Its orbit has the potential to get altered again. It potentially gets less eccentric as it goes through more orbital iterations, and that's what we refer to as dynamically old comets, or short period comets, Jupiter family comets, comets that are more confined to the inner solar system. And so this description of the architecture of where these comets are in our solar system, there's different types of families, right? And so the Oort cloud comets, those are the ones that I study. Those are also known as long period comets, or LPCs. They have the longest orbits. 200 years is kind of the lower end of that orbital kind of timeline. And I think their orbital period can be as large as millions of years. So I like to call these objects once in a lifetime objects once in a human lifetime objects, because once you observe them coming around perihelion for a couple of months or a year, and they go back out of their orbit, you basically never see them again in your lifetime. Of course, you can commission your future generations to observe this comet. You got to really plan down the line, though, because that's going to take quite a while, because it's on average thousands of years. So, and I like to give everyone a sense of scale for how far the Oort cloud is away from us. And so, if we all recall, the Earth-Sun distance is 93 million miles. That's 1 astronomical unit. And if you go out to Jupiter, 5 astronomical units, 500 million miles roughly. Go out to the Kuiper Belt, 50 AU, which is 5,000 million miles. And then if you go way out, before I go out to the Oort cloud, the Kuiper Belt, that's where Pluto is, and I think I heard some discussion about whether or not it's a planet. I personally think that it was promoted to a dwarf planet, because I actually think those are much cooler than regular planets. So, so it's okay to me that it's not a planet. But yeah, so all the Kuiper Belt objects exist in that kind of dusty donut of the Kuiper Belt, 50 AU approximately speaking. And then as you get further and further out, you get to 10 to the 5th AU. So now we're thinking 10 to the 5th times 93 million miles. Can't even, you can think about how that's really quite a road trip to get out there. So another nice sense of scale I like to give in terms of how big comets are. 1 kilometer is about the kind of average radius size of a long period comet or just a typical comet. The largest comet is on the order of 100 kilometers. And if we're looking at kind of the largest axis of like the largest landmass of the United Kingdom, the average comet is about 1/1000th of that diameter. And then the largest comet is about 1/3 of the UK. And then since I lived in Hawaii for the past 8 years, I like to always bring up that I used to be an outrigger canoe paddler, and I actually paddled between 2 different Hawaiian islands that was about half the distance of the size of the largest comet. So yes, that's my humble brag of the day. So of course, I think we've heard today, what's the purpose of studying comets and tracking them and using professional telescopes, using amateur telescopes. And well, the first answer to that question that's obvious is it's just cool, right? It's really cool to see moving objects and images, and they're very spectacular looking. But of course, there's another reason for that, and that's the big picture kind of reason that we study and collect properties for these small bodies. And that's because long period comets specifically, but also in general, this is true for comets in general, but especially true for long period comets, is that these are kind of what I like to call vehicles to the past. And that's because they were kept in cold storage in the Oort cloud for billions of years. Usually when we're measuring their properties, like the kind of ice, what type of grain families, what grain sizes exist on the surface, what the interior looks like, we're probing into kind of the region of both dynamical evolution of the orbit and also primordially where do these small bodies exist in the original protoplanetary disk. So when we study like a large population of LPCs, for example, and we study their properties and if there's any trends between them, we're looking back in time to those early formative processes of the solar system. And so that's kind of the big picture reason connecting it to solar system formation. And so one thing to do to systematically collect observations of a large population of comets, and in particular long period comets, is to kind of have a setup system, which is what I did for my PhD thesis in Hawaii, but it's work that I continue to do, and it's kind of a system that benefits from collaborations across the world and across both professional and amateur observatories. So originally for my thesis, I had a 3-year program that utilized both Gemini North and South and the Canada-France-Hawaii telescope, which are both large telescopes. So for example, Gemini is a 8-meter main optical component telescope, so 8-meter diameter mirror. You can imagine that's really big. So it's able to kind of, it's optimized to look at comets that are far out in their orbits and faint as a result. And so combining that with stuff like all-sky survey data and smaller telescopes that can measure a comet that's closer to perihelion, that's brighter. And so the idea was to have a 3-year program to see how a comet's brightness evolves over time, over the course of its orbit, and so measure a comet's brightness at different epochs in its orbit multiple times, and kind of see how that, see if there's any properties kind of consistent within this population when we analyze that data. So these pictures are just examples of comets observed with CFHT and Gemini to give a sense of scale. I think if you kind of look at the central kind of like part of, let me see if I can use this here. Can you guys see that? Okay, well, hopefully you can. But if you kind of look at this area right here, or like the central region of kind of the coma of the comets, it's about a 5 arcsecond aperture. And so basically what I do is I use aperture photometry, measure the brightness in a given angular diameter, and then I see how that brightness evolves over time. And so in Hawaii, I used telescopes on Mauna Kea, but here I use telescopes on Lucia in in Chile, and so that includes the Danish telescope, the NTTN, as well as the VLT. And so that process I just described here is kind of shown here. So a comet is discovered by an amateur observer or an all-sky survey. And then what happens is I would do cue-based observing, so observing where I would say, hey, can you observe this comet within the next couple of nights? And basically an observer at the telescope would do it for me. So it takes a little bit of the excitement out of traditional night sky observing, but then the next day I wake up refreshed because I don't have to stay up late and to observe the object on my own, but the data is there available for me. So when a comet is going through its orbit, when we're constructing a light curve, magnitude is on the y-axis, and then usually what's on the x-axis for most of my plots in this talk will be what's called true anomaly. It's just a way to orient perihelion as 0, and then all the negative values are pre-perihelion, positive values are post-perihelion, or the outbound part of the orbit, okay? So as a comet's going through its orbit, it will get brighter because of the outgassing that will get more prominent, the dust tail. When we're measuring the brightness contribution from the dust tail and the nucleus in an aperture, that will cause the brightness to increase. And then as it goes outward, it will get fainter and fainter, and that's when it's more optimal to use the larger telescopes. And so this is kind of a nice compilation of both CFHT and Gemini data of this comet itself getting activity that's much more prominent. And again, when we look at these images, you can imagine around kind of the middle images around the coma, that's about 5 arc seconds. And so this is a very small field of view of faint objects that we're talking about. Another thing that I mentioned was I use also all-sky survey data. And so, for example, shown here is assassin data. I forgot what assassin stands for, but it's one of those all-sky surveys that kind of is primarily geared towards measuring transients or like supernovae, for example. But it can also do aperture photometry for comets. And one thing that's useful for all-sky surveys is to provide kind of filling in the light curve itself with data. The downside of using all-sky surveys is usually they have kind of an automatic routine that just gets us the aperture photometry without the images, so there's no way to visually inspect the images themselves. So that's just the downside. And the other downside is most of the all-sky surveys that are available now, with the exception of LSST, which will definitely increase this limit, but most of them kind of break down at magnitude 17 or 18. So yeah. And then the thing that's really helpful for our brighter targets, so for example, this is C2022E3, and this image is taken from arith.net. I'm sure many of you are familiar with this website. It's a really great amateur astronomy website that was put together by Seshi Yoshida, a really great astronomer. And so one thing to keep in mind is that for bright comets, we essentially cannot use the larger telescopes to observe them near perihelion. And so actually getting aperture photometry from smaller observatories with wider fields of view is a bit more optimal and is actually something that's preferred because it avoids the saturation of CCDs for the larger telescopes, and it's generally not possible. And so kind of this green region is where, for this particular target, is kind of where it's optimal to get amateur observations. And so there's a really nice synergy between when we want to construct our light curves, getting amateur observations of our brighter targets when they're near perihelion, and then combining that with observations from our larger telescopes when the comets are further out in heliocentric distance and much fainter. And so adding those two things together along with the all-sky survey data gives us a really nice comprehensive light curve. And then I put here, faint targets, targets in the future. I think you don't need to necessarily discover like a comet, like you don't, I think there's a lot of like A/ observations of targets that exist. For those of you who don't know, usually C/ refers to like a long period comet orbit, but sometimes you have A/ objects, which are like comets that are on long period, objects that are on long period comet orbits, but they're not active. I think they have new rules that if you are the first person to report activity to the Minor Planet Center, the IAU, that actually you can put your name on the end now. So you might want to look that up, but that is something that I heard recently. So might be something nice to capitalize on. Yeah, so this is an example of one of the cleaned up light curves of a comet. This comet's a little bit too faint for amateur photometry, but you can see that a combination of both all-sky surveys and the professional telescopes is really nice to kind of fill in the light curve. One thing to note is that this light curve is kind of dominated by geometrical effects, and that just means that as you're like observing a comet and tracking its brightness over time, you're also on Earth, and Earth is revolving around the sun. So, and a lot of the times when comets are far out in their orbits, they're moving very slow. So usually, sometimes years pass, and that's what kind of causes those little wiggles in the geometry in the light curve. So what do we do after we put together these comprehensive light curves? And the answer is that when you have a comprehensive light curve, you can apply a model to it to retrieve cometary properties. And so originally, this was the Meach et al. 1987 sublimation model. And so the idea is to calculate the, is to numerically solve the energy balance equation at the surface of the comet as the surface of an icy body exposed to solar heating as it goes throughout its orbit. And you're able to calculate the contribution to the brightness from the dust production through a given aperture from the nucleus as well as the dust coma itself. And so that's what all these fancy equations are showing here. But essentially what you had was you had your light curve, you had your model, and you would input cometary properties and try to fit the model iteratively and manually to the light curve. And this was a very robust way to retrieve comet properties like nucleus size, the fractional active area of sublimating ice, what kind of ice is present. But the problem with this was that, is that it's very time intensive. For one comet, it takes many months because you have to go through different possibilities to get kind of the realistic set of parameters, and there's no statistics involved, unfortunately. So a large forming component of my thesis was to develop the VAMP, which is Volatile Activity Monitoring and Prediction Tool. It's essentially the original model plus added statistics, as well as it's fully rewritten in Python. And if any of you know anything about programming languages, that's that took quite a while. And then another thing that I added to was statistics, so the integration of Bayesian statistics as well as temporal parameters that keep track of non-typical sublimation. So for example, if you have outbursts, and I'll explain this plot in just a moment, it'll come back. If you have like a comet with outbursts that last like for a month at a time, for example, the black line refers to the nucleus size, the blue line refers to, the black line refers to the contribution to the brightness from just the nucleus. The blue line refers to the contribution from the coma plus the nucleus. And you can see we can simulate different situations like outbursts or gradual fading or the delay in onset of activity. And so that's a way to kind of quantify and parameterize more complicated thermal processes that are happening on the nucleus with just like the time of the events that are occurring. And so I mentioned Bayesian statistics. I think I'm running low on time, but I'm not actually sure. Okay, I'll just keep going. But yeah, so Bayesian statistics is basically you have all of your input parameters that you're inputting into the model, and instead of iterating through different parameter solutions, you're making the computer do it for you, basically. And so you have like a certain set of walkers, like 16 walkers. Those are like 16 people trying out different solutions for a certain number of steps. And so, for example, 16 walkers, 10,000 steps. They're iterating through different parameter possibilities to construct the probability space of each of the unique parameters. So for example, if you're trying to find the nucleus size of the comet, if you're trying to find what kind of ice is on the comet, when this ice began to sublimate, that can all be searched for at once in a simulated way, in a very systematic way. And it does about hundreds of thousands of simulations, so you don't have to. So it does take up a couple of hours for the computer to do this, but it's a way to kind of systematically recover these parameters. So this is an example of like the random walk of the 16 walkers for 2 different parameters. Nucleus, sorry about the overlapping text, but nucleus, and for example, the fractional active area of water. It explores the parameter space for a certain amount of time, and then it settles in on a solution which gives you kind of an uncertainty as well as an average for the best fit solution. So all of this is to say that you get statistics, you get correlations between 2 different parameters, and you can also recover like the average and the uncertainty in a very systematic way without having to do it yourself. So this is, for example, for just a model that just has 2 model-free parameters, but we also run models that are much more complicated here. So this is like a jump scare of what we call a corner plot, and it just shows the correlations between all the different parameters that you can simultaneously look for. And so this is an example of kind of what that simulated run looks like for the light curve itself. So it feels like this is falling off, but that's okay. Basically, you have like the light curve itself with kind of the bin data just for clarity. You have the contribution from the nucleus, the contribution from water, CO2, all simultaneously fit at once. And kind of the gradient itself refers to kind of the uncertainty of those parameters. And so essentially what I'm still working on right now is publishing these results. But what's really helpful is having kind of, as I've stated before, a collaboration of kind of different data sets combined to create a light curve. And so right now I'm focusing on short period, recovering properties for short period comets that had cometary properties measured by in situ spacecraft. So we're trying to recover those properties just from the model, and we know they're reliable because they were measured with spacecraft. And the idea is to do that, publish that, and then make the model available kind of publicly through GitHub so that other people can use it. So if you have your own like light curve that you want to apply the model to, you can do that, and that's kind of something that's in the works for 2026. Yeah, so this is just an example of, you can also input priors. So for example, if you have dust production rates or gas production rates independently measured with spectroscopy, you can add that as a prior to the model and kind of have more realistic or more informed results from the simulated run. And that's what we did here for 19P. The one on the top here is kind of what we would expect the model to look like in comparison to the data. And then after we include priors information and we run the simulated model, we can recover kind of that realistic situation. And so that's kind of something that I'm hoping to make publicly available in 2026, hopefully. So I'm gonna go ahead and end off with saying, and reiterating that there's a huge synergy between having amateur kind of observations of bright comets closer to their perihelion. And if you're wondering what kind of observations are useful to have this, to apply modeling to in the future, it's broadband photometry, preferably in the R band, but actually visual observations are good too. And if for photometry, there's a lot of publicly available kind of databases, like using the PanSTARRS database to calibrate your images. That's something that I do. You can take multiple images to kind of, as many of you know, look at the dust morphology, and understanding the grain size distribution can also be a prior for the model as well. And then lastly, narrow CN filters are also valuable because it gives you a proxy for the water production rate, which also can be applied as a prior for future modeling. So hopefully when the model comes out, people can use it and get properties for their comets, and we can start seeing if there's any trends for these active bodies. For me, long period comets are closest to my heart, so I really only care most about that population, but of course the short period comets exist and they're also valuable too. And with that, I'll take any questions. Thank you.
Thank you, Erica. And I think it's one of the things that we as comet observers, we're discussing all the time, is the best ways that we do photometry of comets. We've recently had big discussions about what wavebands we should be using, and Sloan R is one of the filters that we're using, and we need to think about how we calibrate those. So really interesting to see how you guys then use that data. So the plan now is we've got kind of half an hour for general questions, but if we could just start with any specific questions on Erica's talk, if anyone has some. Bill, hang on, just bring the microphone around.
Hopefully people can still hear me if I hold it like this. I've given up with...
Hi, thanks. That was a really interesting talk. Can you tell us what actual technique do you use to measure the grain size?
Yeah, so for the specifically for the model itself, the grain size is kind of a property that is currently fixed as like the dominant grain size. I think future work could be to add like a type of power law for the grain sizes to be a bit more realistic. But outside of the model, one could apply like a Finson-Probstein type of like dust modeling to like deep images of the tail to kind of recover the dominant grain size to input as a prior to the model itself. So you're an assumption of the size? Yes, yeah. And so for a lot of the ones I showed here, I think I assumed about micron-sized grains as the dominant grain size, yeah.
Okay, Dennis.
You've shown an example there of a light curve taken from Yoshida's website. Is there any other light curve that you choose to do before for the modeling?
Yeah, so there's a lot of different websites I use. That was kind of the one that shows like a compilation of a lot of the observations, I think, from the Minor Planet Center. I actually directly take from the Minor Planet Center itself. There's a very user-friendly Python-wrapped astro query, kind of MPC astro query that I use, that basically where I recover all the observations for short period comets for a given apparition or for long period comets that have ever been taken, and it tells me like what observatories they're from. And one thing I didn't mention too was that when I was testing my particular tool out, it actually the scatter of the observations, even if there is a large scatter, like if you're using Minor Planet Center data, that's not actually that much of an issue. It's only an issue in terms of computation time because it usually takes a lot longer to run. But Minor Planet Center observations can be used for the modeling.
So the MPC data will be data that's usually obtained when people are doing astrometry, so it'll be in fairly small photometric apertures, won't it? So the photometry that you're on that plot there, I guess, is more total magnitudes, so they're in much larger photometric apertures. So which are the ones you prefer for your modeling?
I think I prefer kind of fixed aperture, yeah, so like around 5 arc seconds. Yeah, I guess, yeah, that's the issue with Minor Planet Center is that you don't really know. It's kind of a compilation of different observations from different sources where sometimes they use aperture photometry, sometimes they don't, and like you said, you don't know what aperture it is. But when I usually, from the all-sky surveys and from my own observations, I use about 5 arc seconds for the modeling, yeah.
Okay.
It works pretty well.
Jonathan, I'm sure.
Seeing as you've sort of raised that point, Nick, the COBS database of visual observations, many electronic observers do put the aperture that they've used as part of the supplementary data.
Oh, that's great.
And so you could use that directly. And I think, Nick, you're working with Yuri to come up with how to code such observation directly.
Yes, that's right. So COBS, I don't know whether you've come across COBS. It's a database of amateur photometric observations of comets. And given that the aperture diameter is so important from a comet point of view, it's a shame that in the past it's not really been encoded in the data sets. And yes, we're working towards trying to make that now a more standard thing.
That's
so,
great, yeah.
Yeah, that's good. So, John.
I may have misheard this, but at the beginning you were saying your major interest is long-period comets coming in from the Oort cloud. But then I thought you said that you were working on this model with short-period comets. Given that the properties of comets coming in from the Oort cloud are so different to the short-period, mainly Jupiter family comets, how will you refine what the model you're developing on short-period comets for long-period ones?
Oh, so that's an excellent question. So one of the methods to validate the model is to validate it against short-period comets, because that's the only ones that we have in situ kind of measured properties for, and that's the most reliable. But another thing that can be done is comparing the recovered properties to other independently measured, like other data sets that also involve modeling, but different kind of modeling. So for example, the NEOWISE data set. So I think there's a set of NEOWISE comets that have modeling that retrieve the nucleus size as well as measurements of the gas and dust production that we can also use that to calibrate against for this particular model. Another thing that I've done that I didn't talk about because because of the sake of time is simulating kind of a cometary light curve for an LPC, a typical LPC orbit, and putting in the simulation that we know those parameters, putting in some typical noise and varying the noise and varying the cadence of the observations, how well we can retrieve those properties for those types of orbits. And so I have run simulations like that on the order of like 1,000 simulations, and there is some for the most part you can retrieve the properties, but there are some limitations that we can discuss after. But yeah, it's definitely something that's challenging, right? Because we've never in situ measured any of these properties for an LPC, and the reality is the properties may be wildly different. So we have to kind of make some assumptions about how we validate the model itself.
Okay, yeah. Thank you.
Thanks, Erica. I think what I'd like to do now